You've probably heard the phrase, a picture paints 1,000 words. Well, it's true in math too. Many mathematical constructs are illuminated by the use of graphs. Hi, my name is Tom Atwater, and today we will learn about the properties of functions through exploring their graphs. Let's take a look at the definition of a function. A function from a set D to a set R is a rule that assigns to every element in D a unique element in R. The set D of all input values is called the domain of the function, and the set R of all output values is the range of the function. Let's look at this with a picture of the idea of what's happening. There is a function, it's a machine of some kind in which we put an x value and it goes through the machine, has some manipulations done to it, and the outcome is referred to as f of x. Well, in terms of the domain and range, what does that mean? Let's take a look. Here we have a mapping, and it's a mapping of a domain to the range, and in this case, this shows a function. And the reason it shows a function is that each element that's in the domain goes to only one element in the range. And even though these two elements each go to the same element in the range, that's okay, because again, there's one going to one. This one is one going to one. But let's take a look at another figure, which is an example that's not a function. And the reason for this? Well, let's look at what happens to x2 is okay. In fact, x3 and x4 are okay. But now, what about x1? Well, the problem is x1 goes off to two different values, which means it's not a unique mapping that's occurring. So this would not be a function. Now, the great thing is there is a test to determine whether a graph is that of a function. It's called the vertical line test. A graph, that is a set of points, x comma y in the xy plane, defines y as a function of x if and only if no vertical line intersects the graph in more than one point. Of course, the best way to take a look at this is to look at some graphs. So, which is not the graph of a function? Well, if I look at this graph here, what I would think about is vertical lines. And is there any vertical line that would intersect the graph at more than one place? And the answer is no, there is not. So that is a function. But what about this next graph that I'm going to show you? What about this? Well, it's very clear that if I were to draw a vertical line here, that it is going to intersect at more than one place. So this is not a function then, okay? Because of the fact that it does not pass the vertical line test. Now, let's look at that domain and range in a little bit more detail. Unless we are dealing with a model like volume of a cone or volume of a box that necessitates a restricted domain, we will assume that the domain of a function defined by an algebraic expression is the same as the domain of the algebraic expression. That's called the implied domain. For models, we will use a domain that fits the situation, and that's referred to as the relevant domain. Let's look at an example. We're going to find the domain of the function g of x is equal to the square root of x divided by x minus 5. Now, what we're interested in, are there any values of x that we are not allowed to plug in to this function because mathematically speaking, it makes it undefined? Well, of course, the expression under the radical may not be negative. So therefore, x cannot be less than 0. What about the denominator? Well, the denominator, x minus 5, we cannot have a denominator that actually equals 0, which means that x cannot actually equal 5. So therefore, if we take all of that knowledge together, that x itself has to be 0 or positive because of the top, the numerator, and x can't equal 5 because it would make the denominator 0, then what we come up with for the domain is that it is going to be the interval from 0 to 5, but it doesn't include 5 because 5 cannot be plugged in, and we're going to union that with the interval from starting at 5, not inclusive, going up to infinity. So that would be the domain of the function g of x. From 0 to 5, union 5 to infinity, 5 is not included. All right, great. Well, now it's time for you to try a problem. And the problem I would like you to do is this. Find the domain of f of x equals the fraction 3x minus 1, all divided by x plus 3 quantity times x minus 1 quantity. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out how you did on this. Now, this expression may not have a 0 in the denominator, right? So right away that tells us x cannot equal -3 and x cannot equal -1. Other than that, there does not appear to be any values of x that are not allowed to be put in to this function, to this algebraic fraction. So therefore, we can write the domain as this. We start at -infinity, and we come up to -3. But we cannot actually put -3 in there because, again, it makes the denominator 0. That union with starting at -3 and going all the way up to +1, neither one can we actually plug in because that is, neither endpoint can we plug in because they make it the denominator 0. And then we're going to union that with starting back up at 1 again, going out to infinity. And so that would be the domain of that function, because those are the values that are allowed to be plugged in. Now, finding the range is often slightly more involved than finding the domain. Graphing definitely will help us in finding the range. On the graph, the x-coordinates refer to the domain, which is what we've been dealing with here, and the y-coordinates are the range. So let's take a look. Find the range of the function f of x equals 2 divided by x. And what we're going to do here is use the grapher to see what this graph looks like. So in the grapher, here's the graph. We have, as you might be able to see, the graph here, and opposite to that, we have this graph. And if we think about this, it appears as though this graph never touches or crosses the x-axis, which again has a value y is equal to 0. And that in fact is true. The x-axis is a horizontal asymptote. And in fact, if we try to solve the equation that 0 is equal to 2 over x, we would not be able to do that. We wouldn't be able to find a solution for which that is equal to each other, each side is equal. So that in fact is the only value that's not part of the range. So to write the range in interval notation, we would write it as such. We would start at -infinity, and it would come up to 0. And both of those are parentheses, because neither of those are actual values that can part of the range. That's going to be union with starting at 0, going up to +infinity this time. So that would be the range of our function f of x is equal to 2 over x. The next topic that I want to discuss with you is continuity. Graphically speaking, a function is continuous at a point if the graph does not come apart or if it doesn't break at that point. let's look at some samples of types of continuity. This is continuous at all points because if I started to trace this graph, there's no point at which I would have to lift up my pen or skip over a point or any such factor like that. So that's considered continuous at all x. The next graph is called removable discontinuity because what happens is as I approach this value of a from either side, I keep coming to this open circle, but as soon as I get there, it jumps up to that value right there. And it's called removable discontinuity because although it looks like it's continuous at that very point, it gets removed. There's another example of removable discontinuity, and that's the same exact picture, but we don't have the value that was up here in the earlier diagram. That's another example, though, of removable discontinuity. And then we also have what's called jump discontinuity. You can see that what happens literally here is when we get to the point A, this part of the graph was coming. It gets there, and all of a sudden literally jumps up and restarts up here. So it jumps from a y value of 0 to that particular y value. And that's called jump discontinuity. All right. And then finally, there is something called infinite discontinuity. Because what happens here is, as we approach the value of a for the x value, you can see that this side of the graph appears to just be going down to infinity. It just keeps going. And as we approach a from this side, this appears to be going up to positive infinity. In other words, chances are we're talking that there is a vertical asymptote here where this is going off to positive infinity, this is going off to negative infinity, and this in particular is called infinite discontinuity. Now, continuity was really easy to explain looking at graphs, and it's more difficult to explain algebraically because essentially what we're trying to do is we want some general point, x comma f of x, to slide smoothly onto a specific point, which we were using a comma f of a, without missing it from either direction. Mathematically, we say that f of x approaches f of a as a limit as a approaches x. So formally, let's take a look at that. Continuity. A function f is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. Now, a function is discontinuous at x equals a if it is not continuous at x equals a. This topic of using limits for continuity and discontinuity we'll get into much later in more detail. But now what I want to do is turn our attention to increasing and decreasing functions. Let's take a look at that. Increasing function. A function f is increasing on an interval if, for any 2 points in the interval, a positive change in x results in a positive change in f of x. Well, let's look at that graphically. What we're saying is, if I start here at an x value of -3, and I move this way, that is positive change in the value of x. Then I'm moving on the graph from here, which has a y value of approximately, let's say, -1. I'm moving along the graph, and look what's happening. I have a positive change in the y value. In other words, a positive change in f of x. And that's true no matter what 2 points I select on this graph. So that was an example then of an increasing function. Let's take a look at decreasing. A function f is decreasing on an interval if, for any 2 points in the interval, a positive change in x results in a negative change in f of x. So let's take a look at this graph. If I take 2 points on this graph, There's my x value. Let's increase the x value, which then brings me to here. What's happening to the y? Well, the y started here, and now it's decreasing to there, which means, again, this is a decreasing function. A positive change in the x value results in a negative change in f of x or in y. All right, what about a constant function? A function f is constant on an interval if, for any 2 points in the interval, a positive change in x results in a 0 change in f of x. A graph, then, of a constant function, a horizontal line. And this would be if I looked at a change in x value, let's say from -1 up to 2, there is no change in the y value. That is, there's a 0 change. It hasn't gone down, it hasn't gone up. And so that's an example of a constant function. All right, let's take a look at combining all of these together. So here's a graph in which it's decreasing from -infinity to -2. So right here, it's decreasing. Then from -2 to +2, it's actually staying constant. That is from right here all the way across to right there at 2. That is a constant function. It's not increasing or decreasing. And then finally, we'll end with the interval from 2 to infinity, where it now is increasing. All right. Now what we're going to do is turn our attention to what's called bound and unbounded graphs. So, lower bounds. A function f is bounded below if there is some number b that is less than or equal to every single number in the range of f. Any such number b is called a lower bound of f. Well, what does that mean? Let's take a look at a picture. Here's an example where the graph is bounded below. What does that mean? It means if I look right here at that value, every other part of the graph is above that value. And of course, these continue on in that direction, so we can see that this is bounded below because of this y value, but it's not bounded above. That is, it just keeps going on to infinity up above. Well, what about it being bounded from above? Let's take a look. A function f is bounded above if there is some number b that is greater than or equal to every number in the range of f. Any such number b is called the upper bound of f. The graph of this, we can see clearly that it's bounded above by this y value. That is to say, the graph never goes above that value. Now, at the same time, this is not bounded below because the graph continues on to infinity at both ends in terms of its behavior. So again, example of bounded above and not below. Now let's take a look at something that's not bounded either above or below. You can see clearly that this graph is going off to infinity in both of those cases, and down here it's going off to -infinity. That is to say, it's not bounded above or below. Well, what about a function that is bounded from both above and below? A function is bounded if it's bounded both from above and below. A good example of this would be a curve that you may be familiar with called the sine curve or the sine wave. The sine curve looks like this, and actually it continues in this direction as well, but its highest point that it ever attains is the value of 1. And the lowest that it ever attains is the value of -1, which means that it is bounded from above and it is bounded from below, and therefore it's referred to as a bounded curve. All right, great. We still have some more to do, and that is called the extrema, both local and absolute. So let's take a look at what that is. We have what's called the local maximum of a function f is a value f of c that is greater than or equal to all range values of f on some open interval that contains c. If f of c is greater than or equal to all of the range values of f, then that f of c is called the maximum or absolute maximum value of f. Local minimum. A local minimum of a function f is a value f of c that is less than or equal to the range values of f on some open interval containing c. If f of c is less than or equal to all range values of f, then f of c is referred to as the minimum or absolute minimum value of f. All right. Local extrema are also called relative extrema, and let's take a look at what that means. Here's a graph. And this was from the grapher. So what's great is you can get this information using the graphing calculator, but you can see that there is a minimum value at approximately negative, when x is just beyond -2. In fact, negative 2.056546. The y value is -24 with some more part of after the decimal point. But the point here is that this is a minimum point. That is, it's an absolute minimum point. Why do I say it's an absolute minimum? Because the graph never goes below that. It's continuing to infinity in this direction, and it's continuing to infinity in that direction. So what that means is that that is an absolute minimum. Now, what about that local extrema that I talked about? Well, let's look and see. We could talk about this particular value being a local minimum because for that particular area, you know, from, let's say, here to, actually we could go however far we want, that is the smallest, the minimum value in that interval. Well, we also have, and I'll do this differently, we also have a local maximum point. If I start someplace like right here, and I cover this graph, you know, all the way to there, let's say. So now I'm going from this x value to approximately that x value. For that interval, from this x value to this x value, that is a local maximum point. So those two are referred to as local extrema. This one is an absolute, in this case, absolute minimum. All right. Well, now we're going to take a look at symmetry. And again, looking at graphs is a great way to first approach symmetry. So we have even symmetry about the y-axis. For all x in the domain of f, if f of negative x equals f of positive x, then this will display even symmetry about the y-axis. Let's look at a graph. Here we go. This is showing us that when you plug in positive x or you plug in negative x, that you get the same y value. And therefore, this has even symmetry about the y-axis. And what does that mean? It means the left-hand side over here is a mirror image of the right-hand side of this graph. Another way to say that is, if we folded the graph along the y-axis, the two halves would meet. Now let's take a look at even symmetry about the x-axis. If we have the point x comma negative y, and that's on the graph, whenever x comma positive y is on the graph, then we have what's called even symmetry about the x-axis. And here's an example of what a graph would look like if it has even symmetry about the x-axis. Once again, if we take, we have the point x positive y, if we also have the point same x value, but negative y, we've got even symmetry about the x-axis. And this time the x-axis is where, if we were to fold it graph, the two halves would meet? Well, there's one more kind of symmetry that we're going to look at today, and it's called odd symmetry or symmetry about the origin. And what this tells us is that for all x in the domain of f, if f of negative x equals negative f of x, then it will display symmetry about the origin. And here's an example of where that happens. Notice that we plug in negative x, and what we get out of it is negative y, or in other words, negative f of x. So this has symmetry about the origin. All right, there's something else I want to talk to you today about, and that's asymptotes. And we've talked about them before, but we're going to revisit them and look at them in more detail. Here's an example of a graph that has both vertical and horizontal asymptotes. In this case, we have a horizontal asymptote at y equals -2, and we have a vertical at x equals -2 and a vertical at x equals +2. Here's another graph. In this case, this is off the grapher, and although the grapher doesn't show you the vertical asymptotes and or the horizontal as the previous graph did, you should be able to see from the trend of the graph that we have two vertical asymptotes, one that appears to be at -1, one that appears to be at +2, and that it appears as though the x-axis, or in other words, y equals 0, is the horizontal asymptote. Well, what does this mean algebraically speaking? Let's take a look at this in what's called limit notation, and that is if the line y equals b is a horizontal asymptote of the graph of the function y equals f of x, if f of x approaches a limit of b as x approaches plus or minus infinity, then that y equals b is that horizontal asymptote. Here it is in the actual mathematical limit notation. The limit as x goes to infinity, as x goes to negative infinity of the function f of x equals b, or the limit as x goes to positive infinity of the function f of x is equal to b. And that would show us then that y equals b or f of x equals b is a horizontal asymptote. All right, what about vertical asymptotes? Well, the line x equals a is a vertical asymptote of the graph of the function y equals f of x if f of x approaches a limit of plus infinity or negative infinity as x approaches the value of a from either direction. And in terms of what that would be mathematically speaking, when we put it in limit notation, it's this. The limit as x approaches a from the negative side of f of x is either plus or minus infinity. Or as x approaches, the limit as x approaches a from the positive side of the function approaches either positive or negative infinity. Okay, great. Now we're going to delve into the last thing called end behavior. And end behavior can be horizontal asymptotes. That's one example of it. And we will check out those in great detail coming up. But end behavior doesn't have to just be horizontal asymptotes. For example, in this particular graph, what's happening is this. As x approaches infinity, that is, as the values of x go off in that direction, then the value of y is approaching positive infinity. And on the other side, as x approaches negative infinity, that means as x values go in this direction, what's happening is y is approaching positive infinity. This could be, for example, the graph of a quadratic equation, one that would give us a parabola, or something like that would be a good example, algebraically speaking, of this graph. All right, well, let's take a look at another graph that exhibits a slightly different type of end behavior. Over here it's doing the same exact thing. That is, as x goes to infinity, y goes to infinity. But what about on this end right here? Well, what's happening this time is, as x goes to negative infinity, as the x values go this direction, the y value is also going to negative infinity. That is, it's going down, down, down. All right, so let's take a look at this graph here. This graph is very interesting because it appears as though something's happening in terms of it approaching a horizontal asymptote. And in fact, that's exactly what's going on here. As x approaches infinity, y is approaching the value of 3 right there. And as x approaches negative infinity, y is approaching the value of 3. And so, in fact, that is a horizontal asymptote for that particular graph. I have one more graph that I want to take a look at with you, and that's this graph right here. What's happening? Well, it's interesting because this time as x goes to infinity, it appears as though this graph is getting closer and closer to the x-axis. In other words, y is approaching 0. And same thing over here. As x goes to negative infinity, it appears as though y is approaching the value of 0. It's coming up from below, but it appears to be approaching that as a horizontal asymptote. So it is true that the horizontal asymptote is the x-axis, or in other words, y equaling 0. Okay, next what I'd like to discuss with you is polynomials and talk about them from the algebraic standpoint. As x approaches infinity, that is, as the values of x get very, very large, then the value of y is going to go either to plus or minus infinity, and as x goes to negative infinity, y will also go to plus or minus infinity, and what it all depends on is the leading coefficient. That would be the coefficient of the term with the largest degree. All right, so that's polynomials. Pretty straightforward, easy to figure out. You look at the leading coefficient. What about functions that are algebraic fractions? Let's take a few different cases. If the degree of the denominator is greater than the degree of the numerator, okay, so the degree in the denominator is greater, then as x approaches infinity, y will be approaching 0, which means the x-axis is our horizontal asymptote. So again, that's if the degree of the denominator is more than the numerator. So let's say there's x squared on the top, x cubed on the bottom. That's this example. Well, what about when the degrees are equal? So the degree of the denominator is equal to the degree of the numerator. In that case, as x goes to infinity, what's going to happen is y will approach some value a, which is a fixed value. In other words, it's a limit. And that's going to be determined by the ratio of the leading coefficients. So for example, if we had 3x squared plus 1 over x squared minus 5, what I'm saying to you is the degrees are equal. They're both x squared, so the degrees are 2. And what in that case we'd do, it was look at the ratio of the coefficients. That's an understood 1 in front of the x squared in the denominator. So that would be approaching a horizontal asymptote, approaching a limit of 3. One more case that I want to look at with you, and that is, what if the degree of the denominator is less than the degree of the numerator? In that case, you have to perform long division to determine the equation that is the asymptote. In other words, as x goes to infinity, y is going to approach possibly a diagonal or a function asymptote. And that'll be determined when you do out the long division. So an example, again, something like that, if you had an x to the 4th on the top, and on the bottom you had, an x cubed, then you can see that this example is we would have to divide the numerator by the denominator, and whatever that result would be, which I'll tell you now, that would give us a x when we divide those. And regardless of what we have over here, I'm telling you now that this would be considered a diagonal asymptote. Wow, you guys did yeoman's work in today's lesson. Great job. So what we did today is we explored properties of functions based on looking at their graphs. And I think you got a great idea that if you look at the graphs of functions, it's a lot easier to tell what's happening with respect to symmetry, continuity, asymptotes, end behavior, and all of that. So be sure to work the exercises that your teacher assigns, and we'll see you next time.